Welcome back to our office. Now we're going to make use of our little discussion we had last time of numerical derivatives to do something useful with a numerical derivative. That's particularly to solve differential equations. So this is a big topic, and we'll do it in parts. We'll even take a break. It's not a hard topic, but we need both to talk about what the words mean so we're on the same page so we can communicate better. And we need to keep it in the context of a practical problem so you realize what all these terms mean. The power you get from being able to understand this and knowing what the terms mean as well is that after today's lecture, or today, maybe tomorrow too, we'll be able to solve any differential equation you run into. Be it linear, nonlinear, first order, second order, fifth order, it doesn't matter. Simultaneous, coupled, we have the same technique, we'll use it every place. So that's the power we're striving for. But before we can get there, we need to talk and understand the terms we mean so that we can apply ourselves to the same problem in the same way. So we're standardizing things. That's what we're talking about. So today I'll talk mainly about words, making sure we can communicate well, and then at the end, the last couple of slides, we'll actually get into whole new material, how we apply this idea to the problem we're trying to solve. And so it'll take us a while. Some of you may want, if you know the words, you may want to jump through, just browse quickly these first few slides, and then get on to the latter part. But if you jump to the latter part, you don't know what I'm talking about, come back. It won't hurt you to listen to my voice a little more. This is the problem we want to solve. So look at look at slide 2. That's our problem. What's our problem? Well, looking at slide 2, you may think our problem is we're paying an artist with no ability to produce figures like this, but not to worry, I'm not really paid very much for these. So the problem is, as you see here, we have a mass M being driven by two forces. We have the force of a spring, which can be any kind of spring we want. We'll do some interesting ones. Okay, so that's a function of x. So x here is the distance from the wall, or the distance from the equilibrium position of the spring, how much the mass is moved from that. That's x. And we have another force. We have an external driving force, here indicated by this arthritic hand, which is a function of time. So this hand is going to move the spring back and forth. Periodic force, it could be anything, but it's a function of time. So we have the possibility of a force that's just a function of position, another force could be a function of position, but certainly of time. So time will be the independent variable, x here will be the dependent variable. So you can have a fairly general problem. Okay? And your problem is, assume this is a one-dimensional problem, so it's not as hard as it could be, and then solve for the position x as a function of time. That's your problem. Okay? So that's not very hard to do. What's interesting here is that when we do this problem computationally, we can solve an arbitrary force just as easy as a well-known simple force. Most of the examples of this type of problem that you'll see in the textbooks, particularly in the physics textbooks, at least the traditional physics textbooks, limits the problem to small x values so the spring is linear, so the amplitudes don't get too large, and then we have a simple harmonic motion problem. That's not interesting to us other than as a test case. We want to see what the world is like. Why did you always study simple harmonic motion? Because you could solve it analytically. We can do much better. So now let's look at slide number 3. Same lousy picture. Okay. But now we want to say, how do we solve this problem? What's the physics theory? Well, the physics theory, of course, is Newton's second law. That's true for most everything in this universe, it seems, which tells us that the sum of all the forces in equation 1 here on this mass is going to be equal to that mass value times the acceleration, F equals ma. Okay? So when we apply it explicitly to the problem at hand, what we have are two forces. We have the external force. We sum that up with the force of the spring, F sub k. K here reminding you that there's a spring constant, and that's equal to the mass times the acceleration. And the acceleration is just the second derivative of the position with a function of time. And now that you see derivatives, you say, hey, I know how to do derivatives. From our last lecture, we can do it all. So we have a spring, We can handle that. We know how to handle the external forces. What we don't know how to do yet is how do we solve a second-order ordinary differential equation, which is what this is. And the answer is we use those approximations we spoke about last time with derivatives, but we apply it here. And now let's take a little break already. Let's talk a little bit about philosophy. And if you're a real good scientist, you might want to leave the room now, because this isn't anything I can prove. What I mean by philosophy here is that if you look at most of the descriptions of nature you find in science, physics, engineering, they seem to be in terms of differential equations, ordinary or partial differential equations. And you can ask the question, why is that? Well, I think the answer is probably because that's how we view the world. It's almost like a religious thing. We've just viewed nature in terms of continuous little pieces, space, time, and since space is continuous, time is continuous, we end up with derivatives. So the laws we use to describe nature are derivative laws for continuous functions. And those also happen to be the kind of equations that we can solve. So because we know how to solve them, we view nature that way. Now with computers, there's actually been a change in science, a change I've been involved with. We can, rather than using differential equations, we can use integral equations. That's sort of a, we'll just say, a more holistic view of nature. Rather than look discretely, you might look at the whole world, and rather than looking at position, you might look at the momentum or the frequency of the system and say that's more fundamental, and life might be simpler that way. It's less concrete, more abstract, easy enough to solve on the computer, and maybe a better way. But as I said, that's philosophy, and we'll get on and try to talk about physics from now on. So let's look now at slide number 4, which gives a real concrete example of the kind of potentials we want to solve. Okay. So as I've been threatening you, we will not do harmonic oscillators because everybody else has done that, and then you don't need a computer. So let's be arbitrary. So let's take as our potential the potential given here as equation 3. V of x is a power, 1 over p, whatever power that is, some constant k, something like the spring constant, times the position x to the power p. So that's it. If p is equal to 2, as we show here on the left, then we have a linear system, and that's known as a harmonic oscillator. Now it's linear because the force is linear, but we'll get to that later. Okay? And what you see is that that's the simple harmonic oscillator. If you let p get large, like p equals 6, then we end up with a potential that looks very much like a particle in the box. Why is that? Well, because if you raise x to the 6th power, when x is a small number, say less than 1, a small number, fraction, raised to a high power is a very, very small number. So the potential is nearly 0 till x, in these natural units, is just about equal to 1, and then it gets large. Okay? So it looks like a box. Nothing happening, a free particle in the middle, and then it hits a very hard wall. What hits a very hard wall? You see, I've said it already, and because I think of it this way, and I didn't even explain what I'm supposed to say. Okay? What I'm supposed to say is, whenever a physicist, scientist probably, thinks about a potential, he or she probably thinks about a ball moving around inside of a box. Okay? So here we have a little red ball, and when we think of the motion of a particle influenced by some potential, we think of the particle just rolling back and forth in this box. So in a simple harmonic oscillator, it would roll back and forth, and the motion would be periodic, and it would be sinusoidal. If this is a particle moving back and forth in a very nonlinear oscillator such as this, it would be a free particle essentially in the bottom. That's why I use that expression. And then it would get up to some height here, and then it roll back and forth. So it would have a different behavior. As long as p, the power here, is even, which is what I suggest you use because it makes the math much simpler. As long as p is even, we have a restoring force. So both of these cases, the force always brings the particle back to the center. And if we have a restoring force, regardless of what else is happening, we will have periodic motion. Periodic just means something has a period, a time, that it keeps repeating on a regular basis. It'll happen here. Sinusoidal means it's sine and cosine functions. That only occurs for the linear case here, p equals 2. Okay, so what about the actual force on the particle? We want to use Newton's law. We need the force. Well, in equation 4 here, we see that the force, by definition of potential, okay, the force is always the derivative of the potential with a minus sign in front. So if we take the derivative of equation 3, and here you can do it analytically, so I've chosen a simple form, then you get, p's come down, the p's cancel, you get a minus sign for the minus sign out front, and you get 1 less power of p. Okay? So what? It's just another piece of algebra. Well, yes, but it's very clever. It's very clever in the sense that if x becomes a negative number and p is even, then p minus 1 is odd. And that means if x is a negative number, it's a positive force, which means if we're to the left here, in, say, this potential, negative x values, positive force brings it back to the middle. But then when we're on the right, we have x is a positive number, we have a negative force, and then that brings it back to the middle. So that's why if p is even, or the force always will be the symmetric, right on the left, right and the left, always directed back towards the origin because it changes sign at the origin. So that's what's so important. Okay, enough of that. So let's look at equation 5 here. That's Newton's law. So this is what we have to solve. We have ma on the right-hand side, the mass times the second derivative. Now we have external force. We haven't specified anything for that yet. And now we have the force here. So this is the problem I want you to solve. It's a nonlinear problem because of x depending on the p minus 1, some odd power, some large odd power. P is 2, it's a harmonic oscillator. So let's look now at slide 5. Okay. So slide 5 will try to explain, and the next one after that, will try to explain some of the terms I've already been using in this lecture without yet defining them. So if you knew everything I was saying and it was all clear to you, you can just go through these pretty quickly. But now why don't you take a look at slide 5. And remember Landau's first rule of education. You remember Landau's first rule of education? No, nobody does. Okay. Landau's first rule of education is that most of education is just learning what the words mean. The ideas are pretty simple by and large, but you have to know what the words mean. Once you understand the words, we can explain things. And I can't communicate with you about solving all these different kind of equations with different properties until we agree on some of the words. So let's look at the first word. The first word is order. We speak of first order, second order differential equation, partial, ordinary. What do we mean by order? By order, we always mean the power of the derivative. So here in equation 6, we have in a very standard form, a form we'll try to use all the time. We'll say this is a first order differential equation because on the left hand side here we only have the first order of the derivative. The right hand side could be a general function of time. It could have any function of y you want, but no derivatives. So this is a first order differential equation. What we call the function on the right here is often called the force function. Now maybe because force begins with F and this function also is called F, but actually because this often has part of it which is the force of the problem. So what we're saying here is F could be linear, it could be nonlinear, it could be anything. It's still first order if the derivative is just first order. So for example, equation 7, we have, what do we have? We have t squared, nonlinear in time, linear in position, t to the 9th, ooh, ugly, y to the 7th, very nonlinear in y, which is one of the variables here, the dependent variable, but it's still linear first order because it's linear in the derivative. So a second order differential equation would be one such as Newton's law, Newton's second law if you want, and there we have ma, so d squared y by dt squared makes it second order. It could have the first order derivative here raised to some power, but it's still second order because we're referring to the order of the derivative, not the power. Okay, that's what we mean. And I've already used the term now, and let's talk about it. There's an independent and a dependent variable. And the way to think about this is the independent variable is the guy you can adjust by hand. You can turn the knobs on the piece of apparatus. You can adjust whatever you want. I can tell you, I want this value of the independent variable, and since it's independent, you can do anything about it. So here, in all these equations, time, or t, which is just a letter, t is the independent variable. We can say at time 1 second, at time 2 seconds, tell me what the position y is. Fine. Y, consequently, is the dependent variable because it depends on something else on time, t, here. And so we can't, just y, I can't say, what time is y equals 1? Give me a time when y is equal to 2. Well, I could say that. It's a free world. I can say whatever I want, but there may not be a solution. Okay, because you can't just, with like a knob, whatever value you want for y as you can for t. Okay, but these are just letters. Okay, they can be anything you want. They're just letters which represent something. So as we see here on the last part of the slide, we can have time, t rather, could be a function of x. What? Time is a function of position? T doesn't have to be time. T could represent temperature, another T word. T could represent humidity. Doesn't have to be H, it's just a letter. You know, you're free to define anything you want. But when we write an expression such as T of X, then we're considering T to be the dependent variable because it'll depend on X, which is the independent variable. Y here could be position, X could be position, X could be something else. They're just letters. Whatever problem we have to adjust it to. Okay, so let's get on to slide 6, which has more words on it. And these are the words: ordinary, partial, initial, and boundary. Take a look. What do you see? Well, you see an empty slide, and that might be a clue. I'm going to fill it up with lots of stuff. I didn't want you to see it and get all worried at the beginning, so relax a second. Okay. What do we mean by ordinary differential equations? Well, I don't know. Maybe we mean these are the plain kind that you just see on the street. But actually what it means is the derivative here involves some variable, and that's the only variable that occurs, the only independent variable that occurs in the equation. So for example, this version of a force law has a first derivative of psi with respect to x. And the equation is only an equation in one independent variable x, and therefore it's an ordinary differential equation. It's differential because it has a derivative. It's ordinary because there's only one variable to worry about. Okay? We'll spend more time in this course on partial differential equations, not this term, but next term. They're very interesting. They are the core of much of engineering. They're the core of much of physics because we don't live in a one-dimensional world. We live in a three-dimensional world with time, at least. Okay, so that's 4 dimensions. And if you believe string theory, maybe we live in a 17-dimensional world, or 16. But anyway, that's why partial differential equations are needed. So here we have, what do we have? Here we have a version of the Schrödinger equation, equation 10, and we're saying that this function psi could be a field, could be a wave function, probability function, is a position of, is a function of position x, position y, and time t, and these are second derivatives. And on the left we have a first order time derivative. So this is partial because it depends on more than one variable. Now if I cover it up here, but it doesn't do any good, you can't see that. Okay, so if we covered up the left hand side, we got rid of the time function. You say, do we have an ordinary differential equation? The answer is no, because it still depends on both x and y. So even without the time, this would be a partial differential equation because it has more than one variable. So that's ordinary and partial. What's left? Math. Okay, these are just terms, but you have to remember, even though computers are big, even though now you can hook together thousands or multiple thousands of computers, you can spend billions of dollars to do it, you still can't suspend the laws of math. And the laws of math still hold, even if we're solving the problem numerically. You have to have so many knowns and so many unknowns to solve an equation. Okay? So if we're solving a first order differential equation, first order reminds you means the first derivative occurs, okay, and it's ordinary, so it's only a function of one variable, then we need to have there's an arbitrary constant that always comes in when we do the integration of the derivative, and that constant is normally taken as the initial value, psi of 0. Okay? It could be the value of the function at time 0 could be the value of the function at any time, but it's one constant that you need, an integration constant. First order equation, you need one constant. If we have a second order equation, such as equation 10, we have two constants. We need to have an initial value, say, of the function, and we need to have initial value of the derivative. So this is like when we solve, what do we solve? Projectile motion. You need to know the initial position and initial velocity. Okay? So that's the second order Newton's law. What about boundary conditions? Well, boundary conditions seem similar to initial conditions. If you think of initial conditions being initial time, and then we have position and velocity, boundary conditions mean we have some region of space. So we have this, I don't know, maroon-colored sort of box here, and we're saying that's the boundary of our space, and we know the solution on that boundary. That's why. So there's another condition we must impose on the problem to satisfy something we know or we impose on the boundary. Okay? Well, if you're solving a first-order differential equation with just one constant and you impose another condition, that makes it very hard. That's an over-imposition, just like having relatives over, and an over-imposition means there may not be a satisfactory solution to the problem. That's known as an eigenvalue problem. You'd have to search to see if you can satisfy all conditions. So a boundary condition for a first-order equation will give you an eigenvalue problem. If you have a partial differential equation, that's something else. Partial differential equations, such as equation 10 here, has several variables, so the initial conditions may not be enough constants to satisfy everything. Then the boundary conditions come in. They give you more constants. And there are books written. People study these things and write papers on what kind of initial and boundary conditions you need in order to satisfy any problem. But basically, it's always just the math. If you have so many unknowns, you need so many equations to determine those unknowns, and that's all we're doing here. Okay, more words. So let's go on to slide 7, where we'll talk about the words linear and nonlinear. How many equations do you see? 1, 2, 3, 4, 6. So we're going to have 6 equations here. But the words are very simple. It goes very quickly. What we mean by a nonlinear differential equation is we refer to the dependent variable, it's not time, say y, position, and we're talking about whether y of t or dy dt occurs to the first power or a higher power. So for example, equation 11 here has dy dt on the left, so it's a first order equation. It has only y of t on the right, so it's linear in y. It has time appearing to some complicated power. That doesn't matter, because time is the independent. We're only talking about the dependent variable. Okay? It's just semantics, but people communicate this way. You have no choice. You learn the language or you get confused. You can get confused even if you know the language. But anyway, equation 12 is an example of a nonlinear equation. Again, first order, in derivative. Here we have a linear term in y. Here we have the nonlinear term in y. So the dependent variable occurs here to the square. That's nonlinear. So nonlinear problems are hard to solve analytically, and therefore you are usually not asked to solve them in your elementary classes. And even if you're asked to, you often can't. That doesn't mean they don't have solutions. It just means they're hard to solve analytically. Numerically, it doesn't matter. Numerically, they're just as easy to solve as a linear problem. So one of the strong points of what we're doing now is we're going to develop techniques to solve differential equations, and they work just as well for linear or nonlinear systems. So we'll free ourselves from those bounds. But we can't free ourselves from mathematics. Okay? And the mathematics, again, tells us if we have a linear system, so a system like equation 11 here, then we have the law of linear superposition. And why is linear underlined here? Why does it always say linear superposition? Well, that's because it only holds for linear system. And it says that if we have two solutions to a linear system, A of t is one solution, B of t is the other solution. And if we make a linear combination of them, which means we add them together maybe with some constant in front, but we don't square them or cube them or quadratic them, if that's a word, then we have another linear combination, and that other linear combination is also a solution. Okay, so that's a law. If it's a linear system like equation 11, any combination of solutions will also be a solution. So this is what we use in Fourier analysis. This is what we use in normal mode analysis. It works for linear systems. What's a counterexample? You've got to turn your head sideways to read that if you're having trouble, okay? Counterexample would be, what if we have a nonlinear ordinary differential equation? So equation 14 here is an ordinary nonlinear differential equation. Ordinary because there's only one dependent variable, one independent variable, time, and first order differential equation because it's only first derivative, but it's nonlinear because that has a y squared in it. So that's a lot of terms, but if you use it enough, it begin to sound like you understand what they mean. Okay, does this have any solution? Well, it's nonlinear. Nonlinear equations are hard to solve. They're hard, but mathematicians can be clever. So if you look at equation 15 and substitute it in equation 14, I'm not going to do that. Do that. Stop now. Go home and do it. Okay, it's a solution. But if you take equation 16 here, a linear combination of equation 15 with just slightly different constants, that no longer is a solution. So that's what we mean. If we have a nonlinear equation, we take a linear combination of solutions, it doesn't work. No longer a solution. So that's the difference when you have linear and nonlinear systems. Anyway, now we are ready to go on and put this all together to go back and solve our problem. So maybe it's a good time to take a break, walk outside, get a drink, and come back. You have a break? You sure you're ready for this? Okay. Whether you're ready or not, now's the time. Okay, so let's go on. Let's look at slide 9. And you see slide 9, what we're going to talk about. Let's talk about the applied math and classical dynamics. So put the pieces together. And we'll talk about a standard form for all ordinary differential equations. So this is the power. It's like the Model T Ford with the assembly line, the standardization of parts. Okay, it makes it cheap. Same thing here. We'll standardize all differential equations, ordinary differential equations anyway, regardless of the order, linear or nonlinear, into one form. And once we have that form, we'll put it inside that box, and we'll learn how to solve equations of that form. And what's interesting, why we have a title here, to remind me maybe, is that we'll use this in applied math as a numerical method. And that's what I saw it first, years and years back. But then also the more pure mathematicians studying classical mechanics, classical dynamics, used exactly the same form for pretty much the same reason. Once you have a standard formative equation, you can prove things mathematically about any equation of that form, and you know it works always. So what you may have thought was a special property of one equation was not. It was just a general property of that kind of function. So we'll talk about it now. So what we have here on equation 17 is all ordinary differential equations have to be written like equation 17. Ooh, that's saying a lot. And what equation 17 has is it has a first derivative of y as a function of time. So we go through this again. I don't know if I can say it again. T is the independent variable, y is the dependent variable. And on the right we have a force function f, which is a function of t and y. Okay? The difference here is, and it's hard to see on this slide, is that both y and f are bold. Okay? So bold means, in this case, that these are vectors. These have multiple components to them. We could draw a little arrow above them, but that might remind you of elementary physics, and mathematicians don't do that. And these vectors are not three-dimensional vectors. They can be any dimension. But that's what we need. So what we have here is we have both y and both f can be a whole column of numbers. And so y can have, using the computer scientist way of counting, which is not how mathematicians count, starting at the 0th component at the top, next component y, and going down to n minus 1. So these are n component vectors, but the last component is n minus 1. A mathematician would start at 1 and end with n, but we have to live in all worlds. And likewise, the force function on the right-hand side has first component, which is f sub 0, or superscript 0 here, and has n components all the way down. So think of these as vectors when need be, and you have to have, if you haven't, go back and do it. You know, on a computer, it's very easy to define an array. Okay, you can use a variable name, you just give it a dimension. Well, that's exactly why this is so nice on the computer. You don't have to worry about the fact that this is an array. You just go ahead and do the math as if it wasn't, and then the dimension can be anything. As you get more and more complicated equations, it just gets more work for the computer, but not for you. Okay? So the big rule here, if you look at equation 17, is on the right-hand side, there's y here. And y has no explicit derivatives in it. Okay? So no, on the right-hand side here, this function f doesn't have any explicit derivatives. Now, and y can be variable names. Now, y, one of the variables, one of the components of y can be a derivative. You just don't write it out that way. You have to define that as a separate variable. If that seems like doublespeak to you, I'll explain that now. Okay. So what we have here, equation 19, is if you write equation 17 out in terms of the components, here written, just showing you two of the components, we have simultaneous, first order, ordinary differential equations. Okay. Linear, they don't have to be, because we can have any power of y occurring here, but they have to be first order because we're only showing the first derivatives. And you may think, Newton's law is second order, how do I solve that? Well, you solve that by being clever if you want, and that's what we'll talk about now. So let's go ahead, slide 10, and we're saying, what do we have in slide 10? We have our ugly drawing here, okay, representing the problem we're trying to solve, and we're saying we need to cast this problem into the standard form given here on equation 21. That's not very hard to do. Okay. So we start off by saying, here's Newton's law. d squared x by dt squared. The acceleration is 1 over mass times the force. And if we compare that to the standard form, we'd say, okay, the right-hand side's not bad, except the right-hand side with Newton's law has derivatives in it, say friction, and it can't be here. And we have second derivatives, not first. So we have some work to do. How do we do the work? Well, that's not very hard. We have to always put it into a standard form. So we have two rules we'll follow. First one's easy. The right-hand side in the standard form equation 21 cannot have any explicit derivatives, okay? And the left-hand side can only have first derivatives. So that's the rules. We have to follow that. And you remember those rules. I'll write it down here. You'll have to go and program it up at some point in your life anyway. And then you have to remember those rules, okay? The method won't work unless you do that. So the first one's easy. We always will define, say, the position x to be the first component of y. And you may have been wondering for the last half hour, how come he speaks of position and he calls it y when everyone else in the real world is smart enough to call it x, and now you're seeing the reason. Because x is just one of the position vectors. We're talking about a more generalized position vector, which we'll call y. So the first component, or the zeroth component, if I'm a computer scientist, will be the position x as a function of t. Okay? We almost always start off that way. You can start off any way you want. This is, the simplest way to start it. And here's the trick. We'll define the velocity, which is the derivative, to be the second component of y. So we've said y must be an array, must be a vector. Its first component is the obvious one, x. The second component, by definition, is a derivative dx with respect to t, which we know is just a derivative of y0 with respect to t. So in equation 23 here is already a little tricky, subtle, but as obvious as can be. It's subtle because we're saying the derivative of y of 0 is y1, but that's just the dynamical form we want back in our standard form. So already have done the hard part, but it's defined to be a velocity. That's it. That's just the velocity. And now we've done the hard part. That's it. All the hard part's done. We now just have to make the substitution according to the rules. So that's what we do here in equation 24 and 25. So in equation 24, we say that, okay, we've defined the derivative of y0, which is position with respect to time, to be y1. So we're writing all these dynamical equations down just in terms of the components of y. And we define the derivative of y1, well, that of course is the derivative of the velocity. That's just the acceleration. But we know that's just d squared x by dt squared. I didn't write it here because I didn't want to confuse it, but we know that is just the force on our function. So we have our standard form in equation 21. The first component of f0 is equal to just y1, the velocity. Because why is that? Because if we look at 23 here, we see that the derivative of y0, which is the derivative of x, is just equal to, by definition, y1. So that's the first dynamical equation is just by definition. The second dynamical equation is just by Newton's law, and lo and behold, we get why this function on the right is called a force function, because it always has one component. In this case, the second component, which is the first in computer science world, but anyway, the second component is always the force, and the first component is the velocity. And actually, in a numerical sense, that's how the world works. The position gets changed not because there's an acceleration, but because something has a velocity, and that causes the position to change. The velocity of a particle gets changed not because there's a velocity. The velocity changes because there's an acceleration, which means there's a force, which is what we have here. Okay? So this, in an abstract, general sense, is how we solve ordinary differential equations. And we put them in this form, and then we have an algorithm that always works for this form, which is what we'll talk about in the next lecture. Okay? So, we're done. I think we will now go on to the next lecture, and we'll show you how to solve this problem.